To determine how our galaxy compares to other galaxies in the universe, astronomers have reconstructed its global chemical composition. Despite the fact that it is not unique, the Milky Way it is certainly uncommon. This is something that alien astronomers could detect, and we can use it to comprehend the peculiar history of our galaxy's formation. Welcome back to my channel. What would an extraterrestrial astronomer think about the Milky Way? Hydrogen and helium have existed in the universe since a few minutes after the Big Bang, but all the other elements, which astronomers refer to as the metals, are produced by stars and stellar processes. The metallicity of a galaxy reveals much about it. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium present in an object. Astronomers use the term metals as a convenient shorthand for all elements other than hydrogen and helium. This usage differs from the chemical or physical definition of a metal as an electrically conducting solid. Even though many of these elements are non-metals in chemistry, stars and nebulae with relatively high abundances of heavier elements are referred to as metal-rich, in astrophysical terms. The majority of elements heavier than hydrogen and helium in the universe are created in the cores of stars, as they evolve through stellar nucleosynthesis. Over time, stellar winds and supernovae deposit metals into the surrounding environment, enriching the interstellar medium and providing materials for the formation of new stars. Therefore, older generations of stars, which formed in the metal-poor early universe, have lower metallicities than younger generations, which formed in a universe with a greater abundance of metals. Depending on the available tools and the object of study, astronomers use a variety of approaches to describe and approximate metal abundances. Methods include determining the proportion of mass attributable to gases versus metals, and comparing the ratios of the number of atoms of two distinct elements to those found in the Sun. There is a direct correlation between metallicity and the presence of a giant planet, making the metallicity measurement of a star an important factor in determining whether a star has a giant planet or not. The relationship between a star's metallicity and gas giant planets like Jupiter and Saturn has been demonstrated by measurements. The greater the abundance of metals in a star's planetary system and protoplanetary disk, the greater the likelihood that the system contains gas giant planets. Planet and their formation is dependent on metallicity, planetary system temperature, and distance from the star, according to current models. The abundance profiles of heavy elements in galaxies impose stringent constraints on galaxy growth and assembly history. As the Milky Way is the only spiral galaxy in which temporally resolved chemical abundances can be measured, it provides insight into the origin of metallicity gradients and their correlation with the growth history of galaxies. To date, these abundance profiles have not been translated into the integrated light measurements required to compare the Milky Way to the galaxy population as a whole. The light-weighted and integrated stellar metallicity profile of our galaxy has been finally measured, with a moderately positive gradient inside a galactocentric radius of 7 kiloparsecs and a steeply negative gradient outside. This integrated metallicity profile of the Milky Way is not unique, but it is not typical of star-forming galaxies of Milky Way mass observed in the various surveys, and it was also simulated in the TNG 50 cosmological simulation. The findings imply that the Milky Way may not have a typical metallicity distribution for a galaxy of its mass, thereby shedding light on the vast array of galaxy enrichment processes. TNG 50 is a cosmological magneto-hydrodynamical simulation for the formation and evolution of galaxies that encompasses a volume of approximately 50 moving megaparsecs, and it samples tens of thousands of galaxies, spanning a broad spectrum of galaxy types and environments. Because of the detailed, temporally resolved observations we can obtain from individual stars, our home galaxy, the Milky Way, provides unique and stringent constraints on galaxy formation and evolution. However, the integrated properties of the Milky Way are poorly understood, preventing a comparative analysis of the Milky Way's properties in the context of the vast majority of galaxies, for which only integrated properties are measurable. Direct measurements of integrated stellar population properties, such as elemental abundances of the Milky Way, are becoming possible with the recent advent of massive spectroscopic surveys, which are mapping millions of stars across the galaxy. Metallicity increases from the center of the Milky Way to a distance of about 23,000 light-years, then plateaus at levels comparable to those of the Sun. The Sun is 26,000 light-years from the center of the universe. At a distance of 50,000 light-years, at the outskirts of our galaxy, the metallicity decreases to approximately 1/3 of the solar level. Our galaxy's high metallicity is unusual when compared to surveys of other galaxies, or simulations of galaxies such as TNG 50. 1% of the galaxies surveyed and 11% of the ones simulated are identical to our own. The difference between the two numbers is a result of survey inaccuracies and the impossibility of creating realistic simulations of the universe. The peculiarity of our galaxy's core may be the result of the supermassive black hole's activity, which may have pushed more metal-rich gas outwards, thereby preventing the formation of younger, more metal-rich stars. And at the galaxy's edge, a collision with a small metal-poor galaxy could have added more pristine material, resulting in a large population of metal-poor stars. If we want to determine whether or not the Milky Way is unique, we must discover methods for comparing it to more distant galaxies. Since astronomers realized a century ago that the Milky Way is not the only galaxy in the universe, this has been an open question. This is the first time we can meaningfully compare the detailed chemical content of our galaxy with the measurements of a large number of other galaxies. The results are crucial for the next generation of comprehensive studies of galaxy formation. These studies will utilize data collected by upcoming large-scale observational programs aimed at the Milky Way or distant galaxies. The question holds, what would an extraterrestrial astronomer think about the Milky Way? Thank you for watching.